recording, and then now you can go.
Okay. So I am a neuroimaging researcher. I focus primarily in functional magnetic resonance imaging, which is a lot of words that say what I do at the end of the day is take videos of the brain. Doing that for a while. That's kind of the standard of the field. What we've been doing is we've been taking different populations of people, putting them in the scanners, taking videos of their brains. It's a huge amount of data. It takes a long time to process. And then after that, we've been able to do groups effects and say this person is more likely to be schizophrenic, or this is why this person is expressing this type of depressive symptom. And it was good work, but there is something really unsatisfying about taking somebody who has a serious mental illness, putting them into a scanner, going through all this effort of classifying and understanding what the problem is, and then doing nothing to help them. At the end of the day, I was still sending them home with a lifetime disease with very little chance of remission or cure. Mental illness does not see the kind of rates that we are seeing in any other health field. So I became really interested in seeing what we could do to change that. And about 5 years ago, neurofeedback came on the scene. And that's something which is turning our field on its head. Now, instead of putting somebody in a scanner and just getting information, when we put them in the scanner, we are using that time as a therapeutic treatment. So how do we do that? We've been working on taking the pre-processing that we used to do offline and doing it online. And we've been able to reduce that time down to 2 seconds, which I know for people that do computation are not very impressed by, but the combinatorics involved, it's a pretty big deal. I guess next slide. So what I'd like to do today is go over exactly what our problem is right now, and then I want to go through rapid prototyping, which is exactly what he had planned. Get you guys into groups, get you guys developing different projects, but the prototyping that I want to do takes exactly 20 minutes, and we are going to stick to that schedule. It's a lot of fun, and I think that it has good results. At 8, I think we can start coding. This is all fuzzy. At 8:45, present the results. 9, definitely go to drinks. Next. So there's 2 problems that we're facing right now. We are in a paradigm where we are looking at the whole brain as fast as we can, getting these hits of images. I take those, and my job is to make sure that that image is the truest representation of brain data that we could possibly get. So my job right now, to really sense what my pay is for, is to make sure that at the end of the day, that single shot image that we're getting does not represent any artifacts. So we take out the respiration, we take out any sort of hemodynamic signals that are not related to cognitive activity. And then in addition to that, we put a mask on top of the brain that allows us to pinpoint little millimeters of activity, take those time points, and co-correlate those. That's my job. On the other end, we're taking all of that back end and we're giving these people just a basic visual stimulus, or we're giving them a basic sound stimulus. And the problem is, it's a bunch of neuroscientists working on this field, so instead of getting great stimuli, we always have really simple, terrible stimuli that are disengaging to the user, and no matter how good our brain signal is, if the people are falling asleep in the scanner, at the end of the day, the therapy won't work. So I've gone over a little bit of what this is. This is what this brain data looks like in real time. This is as fast as we can get it. Individual sits in the scanner, we take it off, we do artifact detection, estimation, and then we give them a feedback signal. Right now, the state of the standard of the field is to take a couple of points in time, co-correlate those, and sort of take a slope difference. That's what my field is doing. If you take these time signals and act on whole networks, what we're seeing is a greater change in a single area of the brain because you're engaging the entire network that it works with than you would be seeing if you were trying to up and down or down regulate a single network. Next slide.
Sure you don't want to spend more time on this one?
I do.
Okay.
Okay.
I can't say that I've totally absorbed. Has everybody else absorbed it?
Sorry, this is, to be honest with you, this is the first time I've given this talk to a non-neurofeedback crowd. I'm trying to gauge. So,
So what is the top representing? Is that a brain? Because it doesn't, it looks like maybe the two halves. What is the gray on the top?
Yeah. So this is what the brain looks like if you oh, is that? No. Yes, that's cool. Okay. So this is what the brain looks like if you take, this is the average of like 20 human brains. If you take it and you inflate it so that you aren't imaging it, you're not looking at any of the curves inside the brain. So when you're looking at something that looks like this bubble brain, if anything that's dark is something that was sort of more medial, anything that was tucked away in the brain originally. And when you're looking at the stuff outside, that's anything that would have been visibly available to you had you physically removed this person's brain. Now this comes from the last study that I did, which was working in autism spectrum disorder. What we had done previously was shown that in a huge population of typically developing individuals and those with autistic spectrum disorder, when you compare those, there's really only a couple of points that come out as being really significant in classifying those differences. So their somatosensory system looks drastically different and underregulated as compared to a healthy control. And some elements of their social networks.
Somatosensory is the part that pulls in information from your external senses, right?
Yes. Yeah, so somatosensory is, in a real sense, sort of tactile function, but it seems to be a lot more than that. Working in a narrative like this would suggest that it's embodied social cognition as well. So what we were finding is that if you look at the time course, the one thing across all of this brain activity that was most significantly different between autism spectrum disorder and healthy control was the fact that the somatosensory system and their social social network systems were completely dysregulated. So we said, fine, this might be a good opportunity to do a neurofeedback intervention. We took individuals with autistic spectrum disorder and we started co-correlating those two regions. We chose a region in the center of the somatosensory, we chose a region that was anti-correlated in the sort of posterior parietal.
So what is the feedback? You have an arrow to the feedback. Is that something that they see while they're in the machine? Or?
Yes, and I have an example of that on the next slide. But essentially all we're doing at the end of the day with this study, we've gone through a lot of work to make sure we know what the differences in these populations are. We're taking these areas and we're just trying to make a clinical population that's expressing something that we don't want them to have anymore. So in this case, these people were entirely blinded to the fact that it was even neurofeedback. They thought that they were in a paradigm where we were just observing their eye movements. In reality, what we're doing is taking an moment-to-moment image of their brain, and if you give me the next slide,
yes,
the next slide, and then you play. No. Well, that's a shame.
We're supposed to be able to
Yes.
play something?
So what you're going to be seeing right now, this is somebody's brain in real time, as far as they can see. So it's a very slow signal. But what you start to see is whenever the brain is sort of this dynamic, undulating sort of sea of electrical and hemodynamic movement. And even at random, occasionally you're going to have the configuration that you want the brain to sort of sit into. So at the beginning, when they first get in the scanner, we do this over a couple of days. At the beginning, they're getting hits at random. The brain just occasionally sits into the right configuration, and we give them positive feedback, which is just this game. We tell them to slowly unveil the puzzle. They have no strategy for doing that. In post reports, when we ask them, what did you think we were trying to study? I felt very bad because one of my participants insisted that we were trying to study frustration in the scanner. It's not our goal. Despite that, we saw positive learning rates, and what I mean by that was we saw their brain connectivity change and look significantly more normal over the course of 2 weeks. So we brought them in, we did 4 neurofeedback sessions, and what we saw was with 2 weeks of interventions, there were behavioral improvements that these individuals weren't showing after 6 months of sort of social intervention. This doesn't compare to pharmacological intervention. We didn't want to study where we had the confounded individuals that were currently on a nutritive prescription. So what we did at the end of each segment was tell them what their score was to give them a sort of incentive to continue trying. But what's fascinating to me about this was a proof of concept study to show that we could do full brain imaging, we could choose multiple regions, we could do calculations on those in real time, and we found that this has been incredibly effective. This takes down the time that we need to do neurofeedback by like 25%, and that's going to move this forward. Because now we can move this into more clinical populations. We can use this for people that we may be able to use this for locked-in patients, and that's one of the ultimate goals. Use this for someone that has nothing but their cortical activity to work with. Next. So what I just showed you is sort of the best stimuli we had to offer in 2016, which is a shame. In reality, what most people are doing is something that looks like this. This is the stimulus that I used in my first study. It was a study that we completed at MIT in severely schizophrenic populations. We were attempting to reduce the auditory hallucinations that they were experiencing because no other pharmacological intervention had worked for them. In 6 out of the 8 participants that did this, just by choosing this region where there's sort of this auditory loop of your sort of where your internal voice comes from, just by asking them to reduce that on the bar every time their activity went down in that area, we had 6 out of 8 of them have reduced hallucinations in a 6-month period, and that maintained itself over a year.
Silence, Mr. Bobbitt.
I thought that was really cool. That's why I continued with this, because we were looking at people that there was nothing that we could offer them to help. And this works. Not only did this work, but this doesn't have this sort of, when you fit people with a pharma cocktail, what happens is there's a lot of interactions, and most of the time these people gain a tolerance to this in a couple of months or years. This is not something where we need to be dealing with any sort of tolerance. We're dealing with the brain's own endogenous activity. When it sits into the brain state that we want, that means that there is a natural coordination of their own consciousness, if we want to include that. There is electrical activity, there's hemodynamic activity, and there's frequencies that are going across the brain that we don't even know how to control yet. We don't need to. If at the end of the day we can teach someone to use their own brain activity, then we should be using that as a first standard of practice. And if that doesn't work, we should move forward to something that's more invasive. But the main problem is we're not representing that information well. So there's a terrible thermostat. Next one. This is also a video. Yes. Here is another version of a thermostat. These are all, this is like the biggest paper that came out in 2014 was a thermostat. Next one. Also a video. This one, they were able to have like a 95% remission rate in smoking from giving them a thermostat. But the problem with all of these is that we're running into something that is not a neuroscience problem anymore. What we have is a brain-computer interface problem. About a third of the people that come and try to do these treatments have what we would call BCI illiteracy. So it doesn't matter what kind of stimulus you put in front of them. It doesn't matter how good the signal is that you're trying to loop them into. About 1 in 3 are not going to show any response, and that's just because we are showing them something that is meaningless to them. It's either meaningless or it's absolutely disengaging to them. Next. So that's something I'd really like to change. In my current study, I've switched it up a bit. I'm interested in creating stimuli which are, beautiful, nice to look at. They have a little bit of an aha moment so that you don't get bored. And I also chose fractals specifically because it allows me to have something that's quick to compute and allows me to have a unique stimulus every time I generate a brain signal. Another challenge that we're dealing with so far in the field, we've only done fMRI. So we've only done this slow moving every 2 seconds per session of your brain signal. Now what we're trying to do at NIH is move to doing that co-concurrently with EEG, CEG. Thank you, electroencephalogram. And what that means is that we are going to be able to give feedback not only on this sort of 2-second chain, but also on a millisecond difference, which is where neurofeedback has been sitting for a long time. But if we have both of those, we can choose a specific region and a specific frequency that we want to be working with to engage in. And that opens up a lot of doors for clinical treatment. The problem is, we have no idea how to represent this. There is only one study that's currently active out of University of Oklahoma where they're attempting to do this, and their best solution, they're trying to look at the amygdala and also look at the frequencies. And in order to represent all of that information, they have their participants looking at 4 different thermostats. And they're not doing eye tracking on them. They don't know where they're looking at. They don't know what information is driving the signal that this feedback loop is going into. So that's something that I don't know the answer to. I don't know how to represent something that changes on a millisecond difference as well as something that changes every 2 seconds, all in the same image. It doesn't necessarily have to be visual either. I'm open to any form of stimulus. I'm open to something that's auditory. I'd be open to something haptic as long as it's not made of ferrous metal. Really, if you guys can think of something that you think would tie in somebody's attention for an hour at a time while they're laying down in a loud scanner, I'm open and interested. Yes. So my challenge to you is to see if we can develop stimuli for this problem that are, 1, clear and observable. It needs to show a progression to these individuals. I think that something that engages you in the learning process is where you see a progression. It can't induce a very extreme, it can't be something so extreme as to be playing like a board game. The problem is, if we're trying to change a brain network, we can't enact another brain network. And if we're doing something that's like hyper social, if we're like trying to have them engage in a conversation, or we're having them solve math problems, when you're doing something like that, what you're doing is reinforcing a network that you're not trying to train. So if you give them a semi-passive stimulus, if they're just looking at something that slowly comes on the screen, that seems to be enough to sustain attention, get the brain to sink into these states, but not to overwhelm and put them into an exogenous attentional state. I also think it's important to have an aha moment, to have something where they think that they have completed something. At the end of the day, the pictures were nice, it kept them engaged, but all of these kids cared about was getting the money from this puzzle game. So if you have an incentive on the back end, you can get them to learn more quickly. For now, I'm working with static images. That's because I'm working with a Python script that was given to me. I'm happy to work on anything that has a calculation that would be less than 40 milliseconds. And I can throw that inside of the script if we want to have something that's sort of continuously changing. But for now, to pilot these on real human data, I would need static images that I can input. And for the future, we are trying to think of ways to communicate this millisecond difference and this second level difference all in the same stimulus. And we have no idea how. So this is the rapid prototyping cycle that I would love for us to go through. I've done this with Tom Chi. He's the dude that came up with Google Glasses. And when he tells the story, there's all this stuff. Doesn't matter how you feel about Google Glasses. At the end of the day, they came up with the initial design from concept to design. They did it in 40 minutes, and they did it by doing this. I want us to get to the end product as quickly as possible. And occasionally that doesn't mean sitting down and writing it up in code. I brought a bunch of paper and pencils that we can use just to do a quick 7 minutes prototype. If you can show me something that looks like a computer screen, take me through, this is what it looks like with upregulation, this is what it looks like with downregulation of brain activity. That's cool. That's something that I can work with, and that's something that we can code in the second half. After that, so you guys are going to get into groups of 4 or less. It looks like we're going to have 3 groups. You're going to do 3 minutes of discussing with yourselves what you want to do, choose one thing to pursue. Then 7 minutes of just making that a demonstrated solution. If you want to draw it, if you want to code it, that's fine. But make sure that at the end of 7 minutes, you can have somebody from another group come who has never seen this design, engage with it, and has an intuitive sense of what that means. So have them go through it. We're going to talk a little bit more in the process about how to sort of give them the blinded user design and start working with it. And then 5 more minutes to go through, revise that, and then let's present it to each other. And if we have something that we want to really work on from there, that's cool. We can also go through this second time with a new combination of people. I found that that's the best way to sort of use human capital in a short period of time. And it's a lot of fun. So
I'm going to say, as we pass around the paper and the pens and stuff, go through, people probably have some questions about what exactly is being asked. So I brought that back up.
yes.
When you say clear and observable progression, you kept bringing up the thermostat. So, and that's a clear progression because you either have one or you're all the way up. And so then you also showed the fractal tree